Welcome back. We are in the process of doing Gauss law and its applications. Now I am going to do divergence theorem derivation, Maxwell's equation derivation, everything one and the same. Okay. So one of the important derivation, please carefully listen. Most complicated work I am going to do. At the same time, Maxwell's equations I am going to derive. So totally we are having 4 Maxwell's equations in our syllabus, even in our definitions. In that, the first Maxwell's equation derivation is here. Now what I am going to do, I took a spherical surface. In the center I kept one charge Q, am I right? In the Gauss law. And the charge Q is emitting the flux which goes in the all direction. What was my aim? Total flux is nothing but total charge. I am going to do the same work here. Find total flux. But the problem is, if it is a sphere, that the total surface calculation is tedious because it is a smooth surface. So to avoid that, let us take a volume which is a cube. Okay, which is a cube. We call it as differential volume. Okay, so differential volume, elemental volume, and it is a cube, rectangular coordinate. In this element, it is a rectangular coordinate. Let us keep this in an axis. Okay, it is just a simple assumption I am going to do. That is, let us take this is x-axis and the y-axis and z-axis. Okay. So that if it is an elemental, very small volume, then in y-axis it should be delta y or dy. Both are same. Mathematically we say dy. Physically we will say delta y. Both are same. Please remember. If I am writing delta y as well as dy, everything is one and the same. Please make a note of that. And it is in x-axis, so it is delta x, and it is y-axis, it is delta z. In z axis. And I told you the sphere we kept a charge at the center. In cube I am going to keep a charge at the center, which should be q. And that is going to emit some electric flux in all directions. The starting point is the initial value. So that initial value I am going to call it as d naught. That naught represents the flux which is at the starting point. That flux is going in all directions. Since it is a cube, it is going in x direction, that is towards the camera, and the y direction and the z direction. So I am going to call this as dx naught in ax direction, that is initial value in x direction, dy naught in y direction plus dz naught in z direction. Okay. So now with this initial setup, let us start a small calculation using Gauss law. What is my aim? Please remember. Total charge I am going to calculate. Okay. What is total charge Q? What is Gauss law says? It is closed integral d dot ds. What type of integral? Closed surface. How you took the surface? You have taken a cube surface which is having 6 surfaces. Okay. So whatever that I am showing here is in front of you. It is front surface, back surface, for you maybe right surface, left surface, top surface, bottom surface. So totally we are going to have 6 surfaces put together is your closed surface. So I can say total charge Q is nothing but integration front side plus integration back side plus integration left side plus integration right side plus integration top plus integration bottom. So what is my derivation is calculate individually all 6 surfaces. Don't get shocked. If you do 2, more than enough, we can reply. Again, don't get shocked. If you do 1, we can replicate to another and we can repeat the same. Okay. So my ultimate aim is calculate the integration for all 6 surfaces. Addition of that is nothing but the closed surface. The result will be total charge Q. Okay. Please do remember. Let us make it as equation number 1. Now, what is your integration front side? That is what I am going to calculate. Okay. One by one we will do. I can say integration front side is nothing but integration d in front and ds in front, because you know the Gauss law is d dot ds. So I am going to do the same work, that is d which is going in ax direction, because the flux is front is remember for this front is going to x axis. Okay, can you please recall, front is x direction, back is minus x direction. Careful, back is minus x direction. Right side and left side is y direction, minus y direction. Top and bottom is z and minus z direction. Everything you should be careful. Please be serious. Dot. What is your ds? ds is nothing but this area, right? This particular area. And that area is delta y and delta z. Multiplication is the area. So it will be delta y, delta z in ax direction. Please remember, the area is dy into dz, that is delta y into delta z. Hello my dear, when I do back side, please remember, when I do back side, even that is also delta y, delta z, but it should be minus x, back side. Okay, going back, this is coming front. That knowledge you should have. Later we will do it. Now, I am not going to do integration because the total integration itself for a smaller length. If you do integration 0 to delta y, if you substitute, result will be delta y. So no need to do integration, result will be the same. For example, if you do integration dx for 0 to x, the result will be integration of dx will be x, upper limit x, lower limit 0, minus answer will be x. Now I am going to do integration dx for dy to dx. If I do, because total length is of dx. Now, if I do like this, if you do integration of dx will be x, upper limit minus lower limit, dx minus 0 will be dx. The result is the same. So, under the situation, you no need to do the integration. Symbolic representation is equal to that. That is, integration for a small length is nothing but the same length. And you know ax dot ax is 1, so I can say d delta y delta z. Since it is in x direction, I made it as x, that is dx. Same I can do it for back side also. Please remember, integration back side is nothing but d back and ds back, and I can do d ax cap dot delta y delta z minus ax cap. Y you should know, that is back side is minus. Okay. So I am going to do the same work. Okay, please take care. dx dot product minus delta y delta. That will be. Okay, we will continue that work later. But I want to present you that front is ax cap, back is minus ax. Okay, sir. In the center there was a charge. It started emitting the electric flux. It was going in all directions, you know, but you are going to consider only front surface, that is dx naught. So I can say your dx is nothing but dx naught. Right? That is x is going in all directions, but you take only front direction dx naught, sir. It is initial, sir, but it started propagating in x direction, you know. So what is that I am going to do? Not only initial value plus, imagine there is a room. I am in the center, that is the charge u is in the center. From the center, half of the distance it is going front side. When I do back, half of the distance it will go back side. Okay. So how much extra it is going? Initial value is dx naught. Extra some half of the distance it is going. That is delta x by 2. Why is delta x by 2? Half, because total is delta x. Its charge u is in the center half. So remaining it will that minus delta x by 2 will be there. Okay, we will do it later. Now, from the center, the initial flux is going. It is going through the front surface. If it is going uniform, no issue. If it is changing, okay, if it is changing, one small example I am going to do. Assume there is a moon. In the center, I am having a water fountain. Okay, there is some water is coming and it is going in all directions. Right now, let us consider only x direction. It is throughout the camera. Center. Okay, let us take the camera is front one, the board is the back one. It is dx naught. Answer B. Total length from camera to board is delta x. I am at the center. My finger is at the center. Water fountain is at the center. Delta x by 2 minus delta x by 2 because back side. Okay. But the water fountain started, it started, water is flowing to the camera. But I am keeping some stone here, I am keeping some blockage here. At the time water will be uniform? No, there will be a change, there may be a change. So, dou dx by dou x. What does that mean? X component having variation in x direction. So, same if you do back direction, again minus dou dx by dou x. That is because of the minus. Okay, that you should know. That when I do in the back side. So, initial fountain water dx naught having a variation in x direction dou dx by dou x for the distance of delta x by 2. Okay, this is the general. This dx, if I substitute, the result will be dx naught plus delta x by 2 dou dx by dou x into delta y delta z. So if you try to multiply this value inside, so what will be the answer? Dx naught delta y delta z plus dou dx by dou x delta x by 2 delta y delta z. Okay, let us keep it pending. Who is the integration different side? Okay, keep it pending. Why can't I try the same here also? Okay, now tell me, who is this dx which is going front or back? It's going to the back side. Okay, so this equation I have substituted here. Okay, so what is the back side? The initial value remains same, dx naught. Instead of going front, it is going back. So delta x by 2 dou dx by dou x going back side, so it is minus. If I try to substitute in this particular equation, the result will be dx naught minus delta x by 2 dou dx by dou x minus delta y delta z. I just substituted. Okay, this dx will be substituted in this equation. So you multiply inside. So what should be the result? Equal to dot minus dx naught delta y delta z. If you multiply here, if you multiply minus into minus plus dou dx by dou x delta x by 2 delta y delta z. Okay, let us make it as equation 2. Let us make it as equation 3. Please recall, my dear, this is integration front and this is integration back. You should know. Now I told you, if you do it for front, the same is applicable for back side. Front area plus ax cap, back area minus ax cap. From the center, positive x direction, so plus delta x by 2. Negative ax cap direction minus delta x by 2. Just a substitution, I got this result. So this is for front, this is for back, you know. Later, I am going to add front and back, because front and back, I am going to add. Now, so we can add front and back. If I add, what should be the result? Please recall. Equation, okay, equation 2 plus equation 3 if I do. So the result will be integration front plus integration back. What will be the result if you add these two? Dx naught delta y delta z minus dx naught delta y will get cancelled. Am I right? These two terms is same. If you add 2 times and 2 and these 2 will get cancelled, result will be dou dx by dou x, 2 cancel, delta x delta y delta z, because this you add 2 times, 2 into this term, 2 cancel. So this is for front and back. So next my question is, why can't you guess why I should do left side, right side, top side, bottom side? I no need to guess. Why can't I do one small work? Front and back is in x direction, dou dx by dou x. Left and right will be in y direction, So integration left plus integration right. I can also guess, so I am going to use the word similarly. Dou dy by dou y, delta x, delta y, delta z. Let us say equation number 5. Similarly, integration top plus integration bottom equal to dou dz by dou z, delta x, delta y, delta z, equation number 6. Okay. So I no need to do the calculation. I can guess similarly all these terms. So please try to recall. Okay. Keep a pause and try to copy down. Then and then. Now, what is my ultimate aim? Adding R will be your equation number 1. So, if I do, we get from equation number 1, total charge Q is equal to, okay. So, let us say total charge Q is equal to addition of all these terms. You have a look first. If you add all these three, who is common? Delta x, delta y, delta z is common. So, dou dx by dou x plus dou dy by dou y plus dou dz by dou z. Because if you add all these three, that is 4, 5, 6. If you add equation 4 plus equation 5 plus equation 6, if you add, if you substitute in equation 1 and take common delta x, delta y, delta z. Okay, so that is the definition for the total charge. Please remember. And who is this delta x, delta y, delta z is nothing but volume delta V. Okay, so I can say Q equal to dou dx by dou x plus dou dy by dou y plus dou dz by dou z into delta V. Okay, so this is nothing but elemental volume. If you divide this particular equation by delta V, if you divide, so answer will be Q divided by delta V is nothing but rho V. Okay, is nothing but dou dx by dou x, dou dy by dou y, dou dz by dou z. Okay, now in case if you take that particular cylindrical, that is cube, if that volume shrinks to 0, if that volume shrinks to 0, what will happen we are going to discuss. And you should know Q by delta V that I made it. And it was from the Gauss law, you remember. So integration d dot ds was the Gauss law divided by delta V. As delta V tends to 0, you will get this particular equation. Okay, you can just recall. Okay, it is closely integration d dot ds. Okay, that is what the idea. So this concept is a mathematical statement. Let us make it as 5, 6, 7. And this concept is a mathematical statement. I am going to call this concept as a divergence. Okay. What is the first? Make a note of this particular point. So, what is the concept behind this particular equation number 7? Is nothing but a divergence. Okay. Make the statement, then we will do the explanation. The divergence of the, please make a note. The divergence of the vector flux density D is the outflow of flux from a small closed surface per unit volume as the volume shrinks to 0. The volume shrinks to 0. Okay. So this is the concept of the divergence. Okay. So what is it we are trying to say? Very simple idea. Okay. Don't get confused with the big statement. Let me take a small ball, a balloon or whatever. Let me make it a ball, football or whatever. Put a hole, fill it with water. Okay. That is a hole. That is a volume, closed surface. Volume, delta V, surface, closed surface, closed surface. If I take the football, put a hole and if you fill it with water, crush it to 0. Delta V tends to 0. If you crush to 0, what happens to water? The water will flush out, right? It will go outside. So if it goes outside, will it not expand from that particular hole, small hole? How it expands? Through the small hole, it expands with the rush, with the speed, because I am crushing this to 0. It expands like anything. We call it as parallel, converge or diverge. We say expand, diverge. That is called the divergence. So what is that way? The outflow of the flux, because instead of water you keep a charge. If you crush that volume, the flux is coming out. Instead of water is coming out, the flux is coming out. How the flux come out is a divergence. The outflow of a flux D through a closed surface per volume as volume shrinks to 0 is nothing but the divergence. That is what we say. How the flux D will expand, change in x direction. Dou by dou x means change in x direction, change in y direction, change in z direction. That is the concept of the divergence. Okay. So I can say divergence of D is nothing but div D. Okay. I can say capital D because it is flux density D is nothing but dou dx by dou x. What do you mean by divergence? This concept is the divergence. That is the charge per volume. As volumes reach to 0, the expanding flux is nothing but divergence D. Dou dx by dou x plus dou dy by dou y plus dou dz by dou z. Okay, is nothing but rho v. Please remember, it is what the equation 7. Now let us keep this concept separately, divergence, and let me include one more concept called vector operator del. Okay, this was a very important concept which we discussed in the beginning of our course. Del. What is that particular del which says variation, change? I told in the beginning itself, I am just a stand constant. Yes, I am changing. If I am changing in x direction, you say dou dx by dou x. Y direction, dou by dou y. If I go up z direction, dou by dou z. If you change in all direction, that is variation of a quantity in all direction, then it is nothing but del. What is a del? Let me give you the definition. Please make a note. Del is a vector operator. Del is a vector operator which defines variation of a quantity with respect to coordinate system. Okay, which defines variation of a quantity with respect to coordinate system. Okay, this is nothing but del. And as per the del is a vector operator, it is a vector. Variation of a quantity, I haven't mentioned the quantity, with respect to direction, coordinate system, x cap, dou by dou y, ay cap, dou by dou z, az cap. This is your del, we should know. This is the aspect of the definition. And I also told what is a d, very long back, it is a vector, which is dx, ax cap, dy, ay cap, dz, az cap. And please remember, my dear, this is also a vector, this is also a vector, both are vector. If I do dot product between these two, because dot product is between two vector, it is also a vector, it is also a vector. Result is a scalar. So, what is del dot d? Okay, that is called the dot product. Is nothing but dou by dou x ax cap, dou by dou y ay cap, dou by dou z az cap dot dx ax, dy ay, dz az. Okay, this is the dot product. So if I do this particular work, del dot d, if I do dot product ax dot dx will be 1. If you multiply dou by dou x of dx, ax dot dx is 1, ax dot ay 0, ax az 0, ay ax 0, ay 1, that is dou dy by dou y 1, ay az 0. Similarly, if you do here also, you will get only az, dou by dou z dz. Okay. So this is your del dot d, which is dou dx by dou x, dou dy by dou y. Okay. So let us say this is equation number 8. You just try to compare 7 and 8. Already the divergence says equation number 7. Now the del dot d is nothing but equation 8. Then why can't I call this as divergence? If 7 is divergence, 8 is also a divergence. Okay. So from 7 and 8, 7 says this is divergence of d, 8 says del dot d. So divergence of d, that is nothing but div d is nothing but who, this is the equation, which is this is the equation. This is mathematically represented as del dot d. Please remember, it is a vector, del also a vector. Since name itself vector, I am not going to mention. Del dot d is equal to dou dx by dou x, dou dy by dou y, dou dz by dou z is equal to, who is he? Rho v. I told you it is a scalar. So it is a scalar, it is a scalar. How we know it is a scalar? If there is no ax cap, ay cap, there is no cap, then it is a scalar. So this This is the divergence concept. From 7 we learned divergence, from 8 we learned divergence mathematics, so we merged. So from 7 and 8 I got this particular equation. So from this, one of the important statement, please remember, this is for rectangular coordinate. Same I am going to repeat for cylindrical and spherical. Not there in the syllabus, I will just give the formula. From this we conclude del dot d, that is divergence of d, is nothing but rho v. Okay, this is very important equation which is called Maxwell's equation. Okay, please kindly make a note of that. What is the Maxwell's equation? Del dot d is equal to rho. But hereafter you should not read like this. Del dot d, no, don't read. What is that? Divergence of d is nothing but rho. Okay, divergence of d is nothing but rho, which means if there is a volume and if charge is inside, charge in a volume, if you press, definitely the flux will come out. Flux will come out as a divergence, that is expansion. Okay. So kindly make a note of this. So from the Maxwell's equation, that is divergence of d is equal to rho v, we are going to derive one small concept called divergence theorem. Okay, what is that particular divergence theorem? Okay, first you make a note of that particular theorem. So please make a note. The integral of normal component of any vector field over a closed surface is equal to the integral of the divergence of this vector field throughout the volume enclosed by that closed surface. Enclosed by that closed surface. So what is the divergence theorem? What is the paragraph? We will see that later. From Gauss law, we know Q is equal to closed integral d dot ds. Okay, one concept you should know. And you also know charge and the charge densities are related as Q equal to integral rho v dv. Okay, remember this is surface, this is volume. And I hope this divergence theorem word I have given in the introduction. Okay, Stokes theorem and divergence theorem, which relates surface and the volume. I am going to do that. This is from the Gauss law. This is from the charge and charge density relation. Since both are related, why can't I equate this particular statement, that is closed integral d dot ds is equal to volume integration rho v d. Then if you substitute this particular Maxwell's equation, closed integral d dot ds is equal to volume integration del dot d, that is divergence of d. So this is volume, this is closed surface. That's all. This is nothing but the divergence theorem. Okay. Please make a note of this and the statement I am just going to repeat. Please carefully listen. The integral of normal component of a vector field, any vector field, here it is called a d, over a closed surface, is equal to the integral of divergence of this vector field. If it is d, here also d. If it is e, here also e. It is applicable for anything. Integral of divergence of this vector field, that is d, divergence of d, through the volume, that is what dv, enclosed by that closed surface. Okay. So that is the statement we are going to recall from the divergence theorem. Okay. Please be careful. If they ask derive divergence theorem for just 4 marks, you can just write on this and the statement. If they ask divergence theorem for 8 marks and 10 marks, you should start from the beginning of this particular video lecture and you should come here. If they ask derive Maxwell's equation, you stop here. Okay, please remember. Okay, derive Maxwell's equation which is related to divergence. Okay, please make a note of that. In the next session, I will give you formula for the Maxwell's equation or the divergence in all other coordinates, and I will do some more problems in this particular divergence or Maxwell's equation. Thank you.